All dogs are beautiful in their own way. That dog is struggling. All right, today you will not feel like that when we get done with this lesson. Okay, so today we're going to talk about the magnitude of vectors a little bit more. We're going to talk about do-it-yourself vectors. Huh. Don't worry about it. And then we're going to talk about the dot product. Okay, now, with that being said, today you're going to need your calculator. So take your calculator out, and let's get started. Okay, so when calculating the magnitude of a vector, as we know in 2 dimensions, we just take and we Pythagorize the heck out of that thing, right? So if I got a vector A that does this, right, it goes 1, 2, 3 units to the right and 1, 2 units up, right? To find the magnitude of that vector, we would just take the square root of 13. And Pythagorean theorem would give us that. Okay, when we get to 3 dimensions, we do the same thing, except now with 3 dimensions. Now I'm going to try to help you visualize that using this vector down here. This is a 3-dimensional vector where we've got movement left 2, up 3, and what I would consider like away from you 1 unit. So just using Pythagorean theorem in general, in the 3-dimensional sense, -2 squared is 4. 3 squared is 9, -1 squared is 1. So it looks like I get a square root of 14. Let's see if we can visualize this. Here's your x-axis, y-axis, your z-axis. I'm going to move left 2 units, up 3 units, and away from us 1 unit. How about that? So as this point, this vector coming out of the origin moves left 2 units, up 1, 2, 3 units, and away from us 1 unit. This can be hard to visualize, but what's happening is that there is a prism formed. Yeah? And this vector travels from the green point to the tail or the head of the 3rd movement. So imagine that moving in this rectangular prism from one corner to the opposite corner. All right, so I could use Pythagorean theorem here. There's a triangle. And then once I get the hypotenuse of that triangle, then I can use Pythagorean theorem there to find the hypotenuse of the 2nd triangle. And I've got my magnitude. There's the magnitude of that vector. All right, so this brings up the topic of what is a unit vector. A unit vector is a vector of what length? 1. Why in the heck would that be beneficial? Well, let's say like I had in the last problem, I had a vector of length root 14. But I want to scale it back to a length of 1. What should I multiply it by? 1 over square root 14, right? So a unit vector, this right here is the notation for unit vector. A unit vector is the vector itself divided by its magnitude. The vector itself divided by its magnitude. So for example, on the last one, I think vector A was, what, -2, 3, 1? Or was it -1? -1. If I want a unit vector in the same direction, A hat, that's A hat, I just take 1 over the magnitude times the vector. Some of you might be like, well, I like IJK component form better. Sorry. Okay, you can do this too. Oh, that should be a hat, not a line. That should be a hat. You just do 1 over root 14 times the IJK components. Done. Unit vector, length 1 in the direction of said vector. Be parallel, just shorter, right? Okay, let's look at an example. All right, so here's vector u. When I see this vector and I start thinking magnitude, how am I getting these numbers? How did I get 1, 4, and 1? 1 squared, 2 squared, negative 1 squared, right? I just take those coefficients, I square them. Oh, I want a unit vector? Well, that's really easy. I just take 1 over root 6 times the vector. I like column form. That's just my personal preference. Is it okay if I wrote it like this? Is that okay? Sure. What if you're like, that's JV? I don't want rational or radicals in the denominator. Well, okay, fine. You want to be like that? What would that be? 3? No. Root 6 over 3. So this would be root 6 over 6. This would be root 6 over 3. This would be negative root 6 over 6. There you go. There's a unit vector in the same direction. I don't care. If you want, that's fine. Yep. You could leave it in this form right here, or that same level in component form with ijk. So what's the advantages of a unit vector? The advantages of a unit vector is if I have length 1, I can easily make it length 5. What would I change? I'd change the 1 to a 5. Boom. Now it's length 5. Oh, I want it length 100. Okay. I can easily do that. You're welcome. I want it length 100, but I want it to go the opposite direction. Easy. Yeah? Okay. Okay, let's move on. All right, now we get to what we've done so far is we've added vectors, we've subtracted vectors, we've multiplied vectors by a scalar. Right? If I multiply it by a scalar, I can extend the vector, I can turn it in the opposite direction, or I can make a unit vector out of it. Now what we're going to do is we're going to multiply vectors. Okay? So here we go. Here's this formula. This formula, I'm not going over the proof for. It comes directly from the law of cosines. Okay, but what does this mean? This right here is the symbol for the scalar product, which I like dot product better. I'm going to use the radioactive hot dog here for a second. This is the dot product. Okay, I call it the dot product. It's also called the scalar product. So the dot product of two vectors is equal to the magnitude of the first vector times the magnitude of the second vector times the angle. What do you think that angle has to do with the vectors? Yeah, the angle between them, right? The angle between them. Okay, so let me manipulate this for a second. Algebraically, I think we can agree that if I got cosine of theta alone, it would be A dotted with B over magnitude of A, magnitude of B, where A and B are just vectors. Yeah? Agreed? Let's just talk real quick about two numbers we know really well with cosine. What's the cosine of 90 equal to? 0. So if the vectors are perpendicular, what's true about the dot product? Yeah, the dot product is 0. Cool? So if the vectors form a 90-degree angle, the dot product is 0. You don't even know what the dot product is yet. You're like, huh? Okay, just wait. We'll get there. I got something for you in a minute. What if the angle between the two vectors is 0? What would that tell us about their direction? They'd be going in the same direction, right? If the angle between them is 0, they'd be going in the same direction. What is the cosine of 0? 1. So that means A dot B, and the magnitude of A times the magnitude of B, these should be equal to each other. Oh. Well, what if it was the cosine of 180? What's cosine of 180? -1. So then it'd just be 1 is the opposite of the other. What would be true if their angles were 180? What direction would they be heading? Opposite direction. Parallel, but the opposite direction. Okay, so parallel vectors happen when the numerator and denominator are equal. Could be opposite of each other, but equal. And perpendicular vectors happen when A dot B equals 0. We'll talk about angle between two vectors in a moment. Okay, here we go. All right, so let's assume the angle between the two vectors is 0. So let's say I have two vectors. Let's say A equals I, or we could say it's 1, 0, right? 1 to the right, 0 up or down. Let's say B also equals I, which would be 1 to the right, 0 up or down. So in this case, what I've got is A dotted with B. Right? We said A dotted with B would be magnitude. What would be the magnitude of A here? Well, it would be 1, right? Square root of 1 is 1. So the magnitude of A would be 1. Magnitude of B would equal what? 1 as well. What's the angle between them? 0, right? Because they're both heading in the same direction. Cosine of 0 is what? 1. So 1 times 1 times 1 equals 1. What? Okay, we'll get there. It'll make more sense in a minute. What do you think J times J will be? It'll be magnitude of A times the magnitude of B times the cosine of the angle between. We're assuming that angle is 0. So this will also equal 1. What is K times K? It's going to be 1. Well, what if the angle between them is 0? What would these all, or 90? This would be magnitude of 1 times the magnitude of 1 times the cosine of 90. Now this is 0, so we get 0. What would J times K be? 0. What would I times K be? 0. I times K, well, that means 1 unit to the right and 1 unit toward us. That's going to be a 90 if it comes out of the origin. It'll make a whole lot more sense in a moment. So here's the proof. Anytime I see a number or a letter times itself, I'm going to get 1. Anytime I see a letter times another letter, I'm going to get a 0. Let's go to this slide and see what happens. I have simplified this slide. It may not seem like it, but I have simplified this slide. Okay, so if I were to take A times B here, would you agree I'd have to do something like FOIL on steroids? So I get 3 there, right? And I have to do that how many times? 3 times. So you'll see I've got the first, the second, and the third time there. You with me? So I'm going to show you why what we did on the last page, go away thing, why what we did on the last page is helpful. Trust me that I've done everything I can right here for you to keep this simple. Okay, so watch what happens. We said on the last page, if it was I times J, J times K, or I times K, we got a 0, right? In any order, doesn't matter. But if we got I times I, J times J, or K times K, we get a 1. Anywhere I see a number or a letter repeated or squared, I'm going to keep it. So I'm going to keep this one. I'm going to keep this one. I'm going to keep this one. Everything else I'm going to scrap because we said that I times J is 0. I times K is 0. J times I is 0. J times K is gone. K times I, gone. K times J, gone. So let's look at the component work here. That would leave us at x1 times x2 I squared, which is 1. X1 times x2 plus, so what would we get? Y1 times y2, remember j squared is 1, plus z1 times z2. And of course, k squared would be said thing. So what if A were 1, 3, 5, and B were -1, 9, 7? Done. If I dotted those, what do I do with the x's? Multiply them. +1 times -1 is -1. How about the y's? 27. How about the j's, or the z's? Yeah, plus 35. So the dot product in this case would be whatever that is, 50, 62, 61. What if this thing came out to be 0? What would we know about the vectors? They're perpendicular. If it came out to be 0. So let's do a little bit of work on an example. All right, so here's A. Before I can find the angle between the vectors, I have to find A dot B, and I have to find the magnitude of A and the magnitude of B. Well, the magnitude of A, I'm going straight right here. I see 9 and 1 and 25. Magnitude of A is 35, square root of 35. What's the magnitude of B? Square root of 4 plus 16 plus 1. Square root of 21. Cool. Square root of 21. What would A dot B equal? Well, that'd be 3 times -2. -1 times 4. 5 times -1. -15. Okay, remember, 3 times -2 gives me -6. -1 times 4 gives me -4. 5 times -1 gives me -5. I didn't really follow my own rules there. I got mixed up. And I get a -15. So what does that even help me do? Well, I know that the cosine of the angle between is A dot B over magnitude of A times the magnitude of B, which comes from the law of cosines. So A dot B is -15. I get magnitude of A, which is square root of 35, times the square root of 21, which is the magnitude of B. And that's going to equal cosine of theta. How would I find theta? Use your calculator. Do the inverse cosine of this stuff, and you get theta. Will you do that for me? And then we'll talk about our answers. Did you get 123 point, no,
Yeah.
6? Is that what you got? Okay, now let me help you visualize something for a moment. If these two vectors, I'm going to put tails on both ends because I don't really care right now, but if vector A and vector B cross at an angle of 123.6, could you maybe argue that they also cross at, what, 56.4? I would take either of those answers due to the fact that, that's a legitimate argument, right? Why do I get this angle instead of the acute angle? Well, where is the cosine negative? In quadrant 1 or 2? Quadrant 2, and that's why the angle that's given to you is the obtuse angle. Right? So if that happens in quadrant 2, I know the angle measures in quadrant 2 are from 90 to 180. Okay, but either would be acceptable. There you go. There's your 123.6. All right, and then your supplement right there would be 56.4. Okay, one more thing I got to talk about before you do this. I'm going to skip these practice problems right here, but we can go over them later. Is this right here. Surds. Surds? What? Okay, so it says find the length of these vectors, basically magnitude, expressing your answer as surds. Okay, I don't know what surds stands for, but it has something to do with radicals. So I think it's like Simplify your radicals. I don't know. Do you know? Oh, you don't. Okay, so it is not necessary to simplify these certs. Oh, so maybe it doesn't mean simplify. Maybe it means sup radicals. Sup radicals. But all I would do here is I would get square root of 10. Oh, nice. Square root of 10. Could I simplify that? No. Doesn't have a even or a perfect square that goes into it. Could I simplify something like this? Sure. 5 root 2. I would prefer simplified surds, if you would, please. Okay. All right. That's your lesson for today. You got about 16 minutes of work time right now, so I would really suggest that you get some work done. Like, subscribe, and comment below. I wasn't going to give anything away other than free knowledge. Free college? Free college! Free college for everybody! On Mr. Tuthill. He said he'd pay for it.